What specific problem does your proposed generative photomontage method address in the context of text-to-image models, and how does it enhance user control compared to existing methods?
The generative photomontage method addresses the problem of achieving user satisfaction in text-to-image models, where users often struggle to obtain a single image that meets all their expectations due to the inherent ambiguity in mapping input prompts to diverse image outputs. Unlike existing methods that rely on trial-and-error approaches, where users re-roll the dice to generate variations, our method allows users to first generate multiple images and then select and composite desired regions from these outputs. This process significantly enhances user control by enabling fine-grained selection of specific parts, such as backgrounds or object features, from different generated images, thus allowing users to create a final image that closely aligns with their vision. Additionally, our approach facilitates the correction of undesired artifacts by enabling users to replace specific regions with more visually appealing alternatives from the image stack. Overall, this method empowers users to leverage the generative capabilities of the model while maintaining a high degree of control over the final composition.
Can you explain how the proposed method works, illustrating it step by step from user input to the final image compositing process?
The proposed method begins with the user generating a stack of images using ControlNet based on a specific text prompt and control inputs. The user then selects desired regions from these generated images by making broad brush strokes indicating which parts they want to keep or replace. Following this, the method employs a multi-label graph cut optimization in diffusion feature space to segment the selected regions while minimizing seams between different images. Once the segmentation is complete, composite features are created from the selected regions and injected into ControlNet, which generates the final image. This process allows for seamless blending of user-selected regions, preserving local appearances and enhancing the overall realism of the final output.
Could you provide a simple example to demonstrate the inner workings of your algorithm, including the user interaction and the subsequent image segmentation and blending steps?
To demonstrate the inner workings of our algorithm, consider a user who wants to create an image of a robot with specific features. The user first generates a stack of images using ControlNet with the same text prompt, such as a robot from the future. After browsing through the generated images, the user selects desired regions by drawing broad brushstrokes on the images, perhaps choosing the robot's arm from one image, the body from another, and the head from a third. Our algorithm then performs a multi-label graph cut optimization in feature space, segmenting the selected regions while minimizing seams between them. Finally, during the blending stage, the algorithm injects the composite features into ControlNet, producing a final image that seamlessly combines the user-selected regions while preserving their local appearances. This process allows the user to achieve a tailored result that aligns closely with their vision.
What are the main theoretical and practical advantages of using your method over traditional approaches, especially regarding user interaction and image quality?
The main theoretical advantage of our method lies in its ability to treat generated images as intermediate outputs, allowing users to select and composite desired regions from multiple images, which significantly enhances user control over the final result. This contrasts with traditional approaches that aim to generate a single satisfactory image in one go, often leading to trial and error processes that offer limited user satisfaction. Practically, our method improves image quality by employing a multi-label graph-based optimization in diffusion feature space, which captures richer semantic information and minimizes seams more effectively than pixel space methods. This results in better preservation of local appearances and realism in the final composite image. Additionally, users can correct undesired artifacts by replacing regions with more visually appealing options from other generated images, further enhancing the quality of the output.
How did you validate the effectiveness of your method? What datasets, benchmarks, and performance metrics did you employ in your experiments?
We validated the effectiveness of our method through a series of qualitative and quantitative evaluations. We conducted user surveys comparing our results against competitive baselines, including interactive digital photomontage, BLD, and MASA CTRL plus ControlNet, asking participants to select the most realistic image and the best blending quality. For quantitative metrics, we computed masked LPIPS and PSNR to measure local appearance fidelity, and we assessed seam artifacts using the seam gradient SG score. Our method achieved the highest PSNR score and the second lowest LPIPS loss across all baselines, indicating superior performance in preserving realism and local fidelity. Additionally, we compared our multi-label graph cut with existing segmentation methods, demonstrating that our approach effectively minimizes seams and maintains semantic coherence in the generated images.
What significant results did your new method achieve, and how do they compare quantitatively and qualitatively with existing baselines?
Our new method achieved significant results in both quantitative and qualitative evaluations compared to existing baselines. Quantitatively, our method attained the highest PSNR score and the second lowest LPIPS loss across all tested baselines, indicating superior local appearance fidelity and overall realism. Additionally, our seam gradient SG score was within the expected range, demonstrating effective seam management. Qualitatively, user surveys indicated that our method was comparable to MASA CTRL plus ControlNet in terms of realism, but outperformed all baselines in blending quality, showcasing our method's ability to seamlessly integrate user-selected regions. Furthermore, our approach effectively preserved local appearances and reduced artifacts, outperforming methods like interactive digital photomontage and noise-based blending techniques, which often introduce noticeable seams and color changes.
Can you discuss some limitations or drawbacks of your approach, particularly in terms of user assumptions or performance in varying scenarios?
One limitation of our approach is that it relies on the assumption of spatial consistency among the images in the stack, which can lead to challenges when the images differ significantly in scene structure. In such cases, users may need to exert more effort in selecting appropriate regions to create a coherent final image. Additionally, our graph cut parameters are empirically chosen to encourage congruous regions, which may penalize seam circumference. This can be problematic for objects with curvy outlines, requiring users to provide additional strokes for finer boundaries. While the graph cut optimization is solved in near real time, allowing for quick iterations, the need for user intervention can detract from the overall efficiency of the process. Lastly, if the generated images do not align well with the user's expectations, the method may not yield satisfactory results without substantial user input to guide the composition.
What directions for future research do you propose based on your findings, and what specific improvements or extensions to your method do you envision?
Based on our findings, future research could focus on relaxing the spatial consistency constraints assumed in our method, allowing for more flexibility when segmenting and blending images that differ significantly in scene structure. This could involve developing algorithms that automatically account for dramatic changes in scene structure during the segmentation and blending processes. Additionally, we envision improvements in the graph cut parameters, which are currently empirically chosen, to better handle objects with curvy outlines, potentially reducing the need for extensive user intervention. Another direction could be enhancing user interaction by integrating more sophisticated tools for refining user strokes, which would facilitate achieving finer boundaries in complex compositions. Lastly, exploring the integration of additional control inputs, such as more detailed sketches or depth maps, could further enhance the model's ability to generate coherent and visually appealing composites.